Okay. This section, okay, 2.6 is somewhat challenging. 2.7 is one of the hardest sections in the entire book, all right? So we're right here on the cusp of word problems, which drive calculus students crazy. Getting this concept will make the word problems a little bit easier, but you got to get this. So let me start out by putting something up here. When I write y equals sine x, and I ask you for dy dx, that means we're treating y as what's called the independent variable, and we're treating x as the other way around. We're treating y as if it depends on x. So x is the variable in the problem. Y depends on it. When we take the derivative, I hope everyone in here could just tell me the derivative of that is what? Cosine x, right? Cosine x. But just pay attention to this little detail. What you actually did, and you may not have even realized it, is that you did the chain rule, okay? Right there you have sine of something, right? Sine of something. So you start on the outside. Derivative of sine of something is what? Cosine of that something, correct? Which is x. Then you go inside and you take derivative of what's inside. What's inside? X. What's derivative of x? 1. Why is the derivative of x 1? Because we're saying what's the derivative of x, right? With respect to x. X was the variable that we were differentiating with respect to. So this last little piece right here, I want you to look at it as being the derivative with respect to x of x, and that is 1. Now we don't need to write that, okay? The answer is just cosine x. I'm not trying to confuse you, but where we're headed right now, you need to make the connection that you are actually going inside there and taking derivative of it, but it's a 1. With me? Okay. So let's now start looking at what today is about. Well, the rest of today. Explicit versus implicit equations. In the CDF video, did anyone watch the CDF for this section yet? 2.6? Okay, I talk about it in 2.6, so if you haven't watched it, definitely want to put that on your to-do list. Watch the video on this, but I'll sum it up real quickly. An explicit equation is an equation where you have variables in it, and you can solve for one of the variables in terms of the other. So like something like x plus y equals 10. Can you solve that equation for y? Yes, right? You could solve this and get y equals 10 minus x. So that way, if somebody gives you an x, you can determine what y is. So this is explicit. Y can be determined explicitly by knowing what x is. And you could have done it the other way around too. You could have solved for x. You could have said x equals 10 minus y, right? And now, x can be determined if you just tell me what y is, right? Okay, let's look at that versus something like this. X squared plus y squared equals 1. Now, can you solve that for y? Well, let's try it. Let's move the x squared to the other side. And I need it to be y, not y squared. So what would I have to do here? Take the square root, right? And whenever you take the square root on both sides of an equation, you must introduce a plus and minus, right? So now, can you tell me what y is if I give you an x? Kind of, right? Like if I give you an x, you're going to give me one of two things, right? You're going to give me two answers, not just one. So you can't explicitly tell me, absolutely, definitely, what y is if I give you an x. But you can tell me it could be two things. Are you following that? So we can't determine one variable exactly from just knowing the other. This is an example of an implicit equation. This is an example of an explicit equation. Now, geometrically, what are these? If I graph this, what is this? This is a line, right? This one is a line. If I graph this, what's this? That's a circle. Radius? No? You've seen this before, x squared plus y squared equals r squared. That's the standard form of an equation. What is going on? That is the standard form of a circle centered at the origin, radius r. This is the standard form of a circle centered at HK, radius r. Conic sections, pre-cal. Usually the very beginning of the semester. Standard equation of a circle. So what is this? It's a circle with a radius 1. Okay, circle radius 1. What's the main difference between those two? This is a function, right? You can look at this as a function because it passes the vertical line test. This is not a function. So let me look at that circle. Let me blow that circle up real quick. If I take that circle and I say, all right, go out right here to this x value, the y value that it could be, we said is actually two different things, right? So there's a y value up here and there's a y value down here. So there's two y values that correspond to one x value, right? So it may look like it's not a function. Let's just, we can't study it. But doesn't it make sense that you should have tangent lines? I mean, isn't there a tangent line here? Isn't there some line that has a slope to it there? And isn't there some line that has a slope to it there? Well, we need to be able to find the slopes of those tangent lines. And we need to do it, we need to be able to do it for things that aren't functions. So that, let's say, can we shut the door? Although I don't know why, that little bit of noise just really bothers me. Let's say that we have, like everything we've looked at up to this point, right? Everything we've studied so far, everything, we've been looking at a function and we've been trying to find the slope of the tangent line, right? Slope of tangent line, slope of tangent line, slope of tangent line. But we've been forced to look at functions, meaning they pass the vertical line test. But in the real world, if let's say you have some, I don't know why you'd ever want to do this, but maybe you have like a bug that's crawling around on the ground, all right? And you want to know its speed at some point, at an instant in time. Then you want to know the slope of the tangent line. Well, if you have a bug and we're looking at it from the top and we let it go right here, it may do this, right? And may do that, and we would be happy because we can look at it as a function. But that bug may just decide to do this. Okay, and then it's not a function anymore. And so, in the real world, you can have all sorts of things that don't behave passing the vertical line test. He may not even come back to the origin, all right? He may just go. But this is obviously not a function. But there's perfectly good concepts of slopes of tangent lines at every single point that this bug is crawling, right? All those red lines make perfect sense, don't they? It's just that I can't lock it in. If I give you an x value, right? If I give you an x, there's actually 1, 2, 3, 4 different tangent lines for that single x value. Do you see that? So how do we deal with situations like this? Well, we have to introduce a new type of differentiation called implicit differentiation. And here it is. Implicit differentiation. I think I will motivate this with just some examples. Let's take x, y equals 1. Now, the power of implicit differentiation is that with implicit differentiation, you can basically differentiate anything. You don't need to solve it for any particular variable. You can take the derivative as long as you have an equation, which is what we have here. The issue is that you have to first determine what it is you're trying to find. Do you want to find here y prime? Is that what I would like? And in this problem, yes, I want y prime. That means I want to find dy dx. That means I'm treating x like the variable, and I'm treating y as if it depends on x. What the hell does that mean? Okay, well, let's get to it. So I look at this right here, and I say I need to do this thing called implicit differentiation. So what you do is you look at each side of the equation, and you take the derivative on each side. So let's start with the easier side. And I like to use a little wavy line to represent the fact that I'm about to do implicit differentiation. I'm not saying that this line equals the next line. I'm saying when you do differentiation, you get this line. You understand what I'm saying? So what's the derivative of the right side? What's the derivative of any constant? 0, right? So on the right side, I get 0. Okay, the left side is the tricky one. And you might be saying to yourself, oh, okay, well, I know what the derivative of x is. It's 1, and maybe that's where you're headed with this. But ultimately, it's a product, isn't it? It's a product. And therefore, you must apply the product rule to the left side. So when you do product rule, it's the derivative of the first one times the second one plus the derivative of the second one times the first one. Agreed? So what is the derivative of x with respect to x? Meaning that if I say what's the derivative of x, if x is the variable, then what is it? 1. Okay, it's 1. It's what it's always been. So the derivative of x with respect to x is 1. So that's going to be 1 times
Y.
What? Y? So y is coming from, we're doing f prime g, right? Product rule, f prime, here's f prime, here comes g. G is y. Plus, okay, this is still from the product rule, what? G prime. So now you're asking, what's the derivative of y, right? What's the derivative of y with respect to x? Y prime. That's what y prime is, isn't it? So this derivative of y with respect to with respect to x is y prime. So it appears right here, y prime. And then times what? Don't forget, x. And that's it. That's product rule. Do y'all see that? That's the product rule on that right there. Yeah?
Is that all we have to do?
Well, what is it we're trying to solve for? What are we trying to find in this problem? Y prime. So get y prime by itself now. Get y prime by itself on one side of the equation. So let me write down what this is. This is, I don't need the 1 out there, right? This is y plus y prime x equals 0. So I could move that y to the other side of the equation by subtracting it. And then divide by x. That's your derivative. Your derivative is negative y over x. Now, what you should notice about this is that this is the first time this has happened. All of our derivatives up to this point have always had just x in them, right? Like our answer was cosine x times 2x, whatever. It just had that one variable, right? And that's because everything we had was a function. So all I needed to know was x, and I could tell you the slope of the tangent line. But I was just telling you that with implicit equations, right, you could have things that aren't functions. So in order to know the slope of the tangent line, you need to know more than just the x. You also have to know the y. You have to know the actual point on the graph. And here, I would be required to have the x and the y to give me the derivative. Does that make sense? Now, there's still a little more to this problem. I'm not done. Yeah, I'm done. That's the answer. But, quickly, does this point live on this graph? Does that point live on that graph?
Maybe.
It's not maybe. It does or it doesn't. That's an x and a y coordinate, isn't it? Does it satisfy the original equation? Is 1 times 1, 1? Yes, so that point lives on this graph. Agreed? Okay, what's the slope of the tangent line at that point? -1. Okay, so whatever this graph looks like, if you go to that point, which lives on the graph, and you want to know the slope of that tangent line, you had to plug that x in right here, and that y in right there, and that would give you the slope of the tangent line. Does that make sense? How about this? How about this point? Does this point live on that graph? Yes, right? Because x and y, x times y equals 1. So if you go to that point on the graph and you want to find the slope of the tangent line, it would be what? So be careful here. 2 on the bottom, 1/2 on the -1/2. So -1/2 divided by 2 would be -1/4. So your slope of your tangent line there would be -1/4. You follow me? See, but you notice you have to know the x and the y coordinate to figure it out? Okay, now I'm going to throw something this is going to kind of piss you off a little bit. All right, so look, you see this problem? Let's say I started from the very beginning. Couldn't I have, before I even did any differentiation, couldn't I just divided both sides by x? And now, couldn't I ask you for the derivative of that? And couldn't we just use the power rule that we had already learned? What's the power rule that we already know? Like if I ask you for y prime here, this is the same as x to what power? -1, so what's the derivative of x to the -1? Negative x to the -2, right? And isn't that equal to -1 over x squared? Yes or no? So I could have done it this way, but that answer doesn't look like that answer, does it? It doesn't look like it. Well, hold on. What's y? Y is 1 over x, right? So what would happen if I replace this y with 1 over x? What would I get? What's 1 over x over, well, what's -1 over x over x? It would be -1 over x squared. So they are the exact same derivatives. I just want to show you that they give you the same answer. And you may be sitting there, you're saying to yourself, you know what, screw that freaking implicit differentiation. I'm going to do this. I like this. I'm going to give you a problem now where you can't do this. I just wanted to show you that it gives us the right answer. Just looks a little different. Okay, here we go. How about that circle? Let's take a look at that circle. Find y prime, and which means dy dx. See, I have to be a little bit careful now when I'm telling you this, because now we've introduced this new type of differentiation. I need to tell you what it is I want you to differentiate with respect to. I need to somehow identify to you what the variable is in the problem, what the independent variable is. And by me writing dy dx, I'm telling you that I'm differentiating with respect to what? X. Okay? So take a look at this right here. Here comes my implicit differentiation. That's not squiggly the way I like it to be. There we go. Now look at that equation. Take the derivative on both sides. What's the derivative of x squared? We've done that 100 times, right? It should just be what? 2x, right? But let's slow down a little bit. It's an eraser squared. What's the derivative of an eraser squared? 2 times the eraser, right? To the first power. The eraser is x. But then times the eraser, times the derivative of the eraser. What's the derivative of the eraser? What's the derivative of x with respect to x? 1, right? So there's really like a 1 next to this, but I'm not writing it. Yes? Then what? Plus. Here's the part. You got to pay attention to this. What's the derivative of y squared? Well, you've got to have my eraser squared. What's the derivative of my eraser squared? 2 times my eraser, right, to the first power. Then go inside. What was the eraser? Y. What's the derivative of y with respect to x? Y prime. So you've got 2y y prime. 2y y prime. Does that make sense or not? I mean, you got to ask questions. If it's very little subtleties here.
I don't understand why it's y prime.
Okay, well, remember, if I'm just looking at x, right? If I ask you this, here's x, right? And I say take the derivative with respect to x. The answer is 1. Here's why it's 1. Because you're doing derivative of x, dx, over dx, which is 1, right? But if I say take the derivative with respect to x of y, then you get dy dx, which isn't 1, but that's what we're trying to figure out. Dy dx is y prime. That's the definition of y prime. Does that help at all? No, that didn't help. Okay. Anyone else need a clarification on this? Am I done?
Wait, I have a question.
Yes.
Could you have written like 2y dy over dx? Or
Yes, you could replace y prime with dy dx. And different books do it different ways, and different instructors do it different ways. I choose to leave, right now I'm leaving mine as y prime, but in the next example I might go to dy dx. Am I done though?
Equal to 0?
Equals 0. Do not forget this is an equation. Equals 0.
Is that it?
Now solve for y prime. You always need to isolate y prime at the end. So to isolate y prime, I'm going to move my 2x to the other side, and then I'm going to divide through by what? 2y.
So can that just be negative x over y?
Negative x over y. Cancel the 2's out. Negative x over y. What does this represent again? I mean, think about what this problem was about. What was it? It was the slope of the tangent line of a what? Of a circle, right? Y'all, right? That's what this was? So check this out. This is actually pretty nice. Look at this. Here's a circle. It was the unit circle, wasn't it? It was the unit circle? Let's just check out these points right here real quick. Let me do this one first. What's that point as an ordered pair? The point up here. 0, 1. 0 for x, 1 for y. What's the slope of the tangent line there? Should be 0, right? It's a horizontal line, but plug them in, right? Negative 0 over 1. 0 over 1 is 0. So you get, that matches, doesn't it? If you go down here to this one, you'll get 0 also because your x coordinate is 0. What about here? 1, 0. You get what? Undefined. Why is it undefined? Because it's a vertical line. Vertical lines don't have slopes. Their slopes are undefined. And so you get that matches up on both ends also. And then if you go to this point over here, does anyone know what that point is right there at 45 degrees? Root 2 over 2? Root 2 over 2. And if you plug those in, right, x and y, what do you get? Negative root 2 over 2 over root 2 over 2, which is negative 1. Slope is negative 1. And if you go and plug that point in, you'll get positive 1. If you plug any point in on the circle, you'll get the slope of the tangent line. It's actually pretty nice. Okay, we have a lot more to deal with here. All right. I don't think we're quite ready for the next thing yet. Here's an example. That'll drive you crazy. All right, on this one, I want us to find y prime. I want us to find Find dy dx. I've got to tell you all this story, but I'm going to wait till after this example. It's been cracking me up like for the last 10 minutes in my head. Okay, let's do this. This is a beast. You cannot get y by itself. There's no algebra that anyone anywhere can do. Okay, no one can isolate y for this. And the reason why is because y is trapped inside of a trig function. And then it's over here. So if you try and remove the y from the trig function, you have to come in with arc sine on both sides. Arc sine will release it from the sine function here, but now you've trapped this y inside of an arc sine. So you algebraically just can never get y by itself. And there's lots of equations where you can't isolate variables. But we still have a way of figuring out what the slope of the tangent line is. So let's be very careful. Let's go through this. Left side and right side individually. Here comes my implicit differentiation. What do you think about the left side? What's that? I heard it. Chain rule. It's chain rule. You have sine of something, don't you? Sine of something. So the derivative of sine of something is what? Cosine of that something. But then chain rule says now you say times, right? Times the derivative of what's inside. And this is why that little shortcut I was giving you a little while ago, for, you know, like with the u and the w and stuff, is real cute and fun. But you can't do that on these problems. So you have to get to the point where you can do it all, it's all happening in your head. So sine, derivative of sine of something is cosine of that something, times derivative of what's in there. Now, what do you see in there? What are you seeing here? You see a product here and a sum there, right? So aren't we going to have to do a little product rule right there? And then plus the derivative of this. So what's the product rule on this? We just did that, didn't we? What's the derivative of x times y? Wasn't it 1y plus y prime x? Let's do it. Here's my product. Derivative of the first one with respect to what? X is going to be 1 times y plus derivative of y with respect to x is y prime. Now I'm going to write it as dy dx just to show you that writing that instead of y prime there's not an issue. Okay? And then times what? X. Are we done? No. That's the product rule, right? But then I need to do plus what? The derivative of this. What's the derivative of y with respect to x? Y prime again. So plus, right? Plus y prime. I'm going to write y prime as dy dx. Now I can close it off. Now I'm done with the derivative inside. You've got to ask a question. I mean, this is so critical, especially in the next section, like I said. You've got to see this chain rule, and in the chain you've got to see that product. And am I done? Nope. Equals, right? Equals. What do we have going on the right side? What do we have here? Product. So what's the derivative of the first one? What's the derivative of 2x with respect to x? Shit, I just said it. What's the derivative of x squared with respect to x? 2x. Times y cubed plus, now I'm doing product rule, right? F prime g plus, now what's the derivative, careful, of y cubed? 3y squared times y prime, which I'm going to write as dy dx. You don't like the dy dx? I don't either, but we should be comfortable both ways. Am I done? What do I still need? Times x squared. Now I'm done. Now you have to solve for dy dx.
That's impossible.
No, it's possible actually here. Because, well, I'm going to have to do it because you need to see one of these. This cosine, right, is being multiplied times that parentheses. So that cosine would go multiply like that, right? And then the parentheses are gone. And on that side, it's just there, right? So watch, when I do this times this, I have to do, well, I did twice. It's 3 times, right? It's 1, 2, 3 distributions there. So when I do this times this, it's just a y, right? So y times that. Y, I'm going to put in front. Cosine xy plus y. Plus, now I have this times that, right? This times that. So I'm going to do dy dx times x times cosine xy plus y. Then what? Then y prime, or dy dx times cosine xy plus y. Does everyone see that that's just distributing this big hunk of junk right here through those 3 terms? And on the right side, what do I have? Just 2xy cubed plus 3y squared dy dx x squared. What is the goal of all this? To try and do what? Get y prime by itself, right? So where are the terms that have y primes in them? This one has a y prime, this one has a y prime, and this one has a y prime. So what do you think I'm going to do? How about I get all my y primes to one side of the equation? Everything that has a y prime to one side, everything that does not have a y prime to the other. Why? Because if I get everything over here has a y prime in it, then what can I do? Factor out the y prime. So my next line, if this looks like an algebraic nightmare, it is somewhat of that. You know, I mean, it's not trying to hide anything from you. This is your reality now. Okay, unfortunately, this is your reality. Okay, so I'm going to write down here dy dx. Does that seem rude? I don't mean it to be rude. I mean it to be truthful. Plus dy dx cosine xy plus y. And then minus 3. I'm going to kind of rearrange this a little bit. So those are the 3 red ones all moved to the left. So when I moved this guy over, it became negative. And then I moved that x squared over there by the y squared. Is that all right? No or yes?
I'll just go.
That's these 2 terms, still on the left side. Bring this one over. Then I'm going to take this one, which does not have a y prime in it, right? And move it to the right side. And it will join up with this one, which was still left over there. So the right side of that equation is, I'm going to put the 2x y cubed first, and then minus y cosine xy plus y.
And that's on the right side?
That's on the right side. Sorry, I'm trying to fit it all on camera here. And it's not working out too good. We're almost there, okay? We're almost there. What I need to do now is factor out, on the left side, factor out, since this has dy dx, dy dx, and dy dx, pull that out. So I'll have dy dx, and then what will be left is x cosine xy plus y, plus cosine xy plus y, minus 3x squared y squared. Then on the other side, we still have the 2x y cubed minus y cosine xy plus y. And what would my last step be? Divide this side of both sides of the equation by everything in parentheses here. And so basically your final answer, dy dx, is going to be this divided by that. And it's a huge, ugly mess. But that's what it is. So I think I obviously turned up the problem, the difficulty there a little bit, right? Do you want me to write the final answer, or is that okay? Just that thing underneath that? Now, I'm going to do another problem here to show you kind of where we're headed. All right. Does anybody recognize this formula? That's the area of a triangle. If you know its what? Base and its height. So if somebody gives you a triangle like this, and you know the base and you know the height, then that's the formula for the area, isn't it? Right? Isn't it? Okay. Here's what I want you to find. This is going to be kind of weird. Find dA dB. dA dB. Find the derivative of A with respect to B. That means that you're going to treat B as the variable. But what are you going to do with the A and what are you going to do with the H? Well, the A, okay, the A is going to be treated like it depends on B. And the H will also be treated as if it depends on B also. So how are we going to get a derivative out of this? Here we go. Watch. I'm going to do implicit differentiation. So both sides of this. What am I differentiating with respect to? B, right? So what is the derivative of A with respect to B? It's the derivative of A with respect to B. That's what it is, right? It's dA dB. Why is that good? That's what I want, right? That's what I'm trying to find, right? That's what it is that I wanted to find. There it is. It will be equal to what? Over here, what do I have going on? Product rule, right? I have a product rule. Now, does everyone agree the 1/2 is a constant and it's just tacked onto this stuff? So I can just ignore the constant and do my product rule right here? So I'm going to throw my constant here, and let me figure out what my product rule is going to turn out to be. So you help me out. I do product rule here. What is the derivative of B with respect to B? What's the derivative of B with respect to B? 1. 1 times what? H, right? Plus, now, what's the derivative of H with respect to B? I don't know. dH dB, exactly. It's dH dB. And then, times B. Following me? Now, just all I want is that right now. We have an equation for this, okay? Let me do another one. Same exact equation. I'm going to ask you for something else now. What is dH dA? What's dH dA? So you start with this same equation right here. So what am I differentiating with respect to? What's the variable in the problem, the thing I'm allowing to change? The capital A, right? So when I go and I look at this equation, I look at the left side, I say to myself, what's the derivative of A with respect to A, right? What's the derivative of A with respect to A? Because we're differentiating with respect to A here. What is it? 1. Equals. Now here's my 1/2 again, and I still have product rule here, don't I? Now you say, what's the derivative of B with respect to A, right? With respect to A. What's the derivative of b with respect to a? Well, whatever the hell the derivative of b with respect to a is. I don't know what it is.
Can we write that as b prime? Or?
See, that's why we can't use prime anymore, is because the prime doesn't tell you this variable, and we need it, okay? We need it. All right, times what? H plus, now, what's the derivative of h with respect to a? dH dA, right? What's good about that? That's what I was looking for, right? That's what I'm trying to solve for, and it has now appeared in my equation. And then times what? B, product rule. Now, couldn't you isolate this? Couldn't you get this on one side of the equation by itself?
Yes.
And then you would have a formula for this, wouldn't you?
Yes.
Okay. This is where we're headed, all right? Are you all right with this? I think I need to give you one last one on this one. What is dA dt? This is super important right here, okay? This is super important, this one I'm doing right now. What are you thinking to yourself right now? This is the first time I've given you anything like this, but what is it that's unique about this problem? T doesn't even appear in the equation. T doesn't appear in the equation. But that's okay. We can still differentiate things with respect to a variable if that variable does not appear. We can still do it. So look, what's the derivative of, well, how do I say this? I'm looking at the derivative of a with respect to t. So how do I write that? dA over dt. That must equal, now the 1/2 still there, right? Here's my product rule. I still have product rule, right? What is the derivative of b with respect to t? dB dt times h plus what? The derivative of h with respect to t, which is dH dt, all over, times b. Now what was it that I was trying to solve for? dA dt, does it appear over there? Yes, here's the equation of it. Now what the hell does all this mean, right? Like what is this all about, right? What is it all about? We're headed that way, okay? I can't exactly, I can kind of give you a glimpse, if you'll allow me to, real quickly, all right? Can I give you just a quick glimpse of this? Let me draw a real simple triangle like this. Base and height. Then the area is 1/2 base times height. Now if I tell you the base is 10 and the height is 6, you can give me an area, can't you? If I just tell you this is 10 and this is 6, that would be 10 times 6, 60, half of that, 30. So this would have like 30 square feet or 30 square inches, right? What we want to know is this. Let's say I start letting this side of the triangle grow. So let me say I start letting B grow. And at the same time, I start letting H grow. And maybe I let B grow by 2 inches per second. So every second it's growing by 2 inches. And I let H grow by 3 inches per second. So now H and B are both growing. Do you all see the triangle changing? It's getting bigger and bigger and bigger and bigger, right? Would you agree that the area is also changing? The question will be, okay, it's going, it's growing, it's growing, it's growing. The area is changing, changing, changing. Right then, when I say whenever that then is, how fast is the area changing? Not what's the area, how fast is it changing? It's kind of like, remember I was talking about you're running and then you say at that instant, right then, how fast were you going? Didn't I do that? Was I running?
Sort of like that.
And yeah, something happened, right? What happened? Was it my watch went off? Yeah, right there. It was pretty funny. So now we're looking at, instead of a linear motion, I'm looking at some geometric figure that's growing, and I'm looking at an instant time, how quickly its area is changing. That's exactly what that formula gives you. It's saying, what's the change in area with respect to time? I think that's my phone, I'm sorry. I thought it was off. What's the change in area with respect to time? Well, it's equal to this. The change in the B with respect to time. That's how fast B is growing. Times the height plus how fast H is growing times the base. that will tell you exactly how fast the area is growing at that instant in time. So I'm just trying to get you led into this. You need to watch the video for both 2.6 and 2.7 for next class, because 2.7, I do a lot of pictures in animations in 2.7 showing you how things work. Let me tell you, can I tell you that story real quick? It's kind of going to be anticlimactic now because I've built it up to be more than it is. But back when I was in graduate school, maybe I should pause the video real quick before I tell you this story.
They earned it after watching the rest of it.
Yeah, no, I'll stop the video real quick. I'm going to have to turn it back.